Assalamualaikum warahmatullahi wabarakatuh. Today we're going to start with a new topic, still under organic chemistry. This is topic number 17. The next functional group that we are going to look at is called the carbonyl compounds. So carbonyl compounds are compounds with the C double bond O, but specifically for aldehydes and ketones only. Okay, so you will see that in carboxylic acid and esters, there's also the C double bond O, but these aren't considered carbonyl compounds. Okay, so carbonyl compounds are aldehydes and ketones only. Now for aldehydes, so for aldehydes, usually the functional group is when you have the C double bond O attached to at least one hydrogen. Okay, so since the C double bond O must be attached to at least one hydrogen, that means your aldehyde will always have the carbonyl C double bond O at the end of the chain. So we call this terminal. Okay, the end of the chain, that means the C double bond O will be at the terminal or at the end of the chain or at the start of the chain. Okay, as for ketones, the C double bond O will be attached to two alkyl groups. So whether it's attached to a methyl group, an ethyl group, propyl, and etc., as long as it is attached to both bonds of the carbon and the C double bond O are attached to carbon atoms. Okay, so and it's important that you know the difference between ketone and aldehyde. So for aldehyde, it's CHO. That's why you notice that sometimes in the structural formula, we tend to write down the functional group of aldehyde to be CHO, and we avoid writing it as COH instead. Okay, it's not wrong, but COH looks like it has a functional group for alcohol, right? But of course, it will not be the same because the number of hydrogen for aldehydes and alcohols would be different. So that's how we usually write the structural formula of an aldehyde, and this is an example of structural formula for ethanol. As for ketones, the functional group is C double bond O attached to both carbon atoms. Okay, writing down the structural formula of ketones is shown here, CH3CO, CH3, so you don't have to write out the double bond, C double bond O. This is an example of propanone, and for ketones, the C double bond is usually in the middle of the chain. Okay, naming ketones, it will end with O and E, like this, propanone, and naming aldehyde, it will end with Al, for example, ethanol. So aldehydes and alcohol, be careful when you name them because naming alcohol will end with OL, whereas naming aldehyde will end with AL. So here are two examples for us to name the molecules. First, I would identify the functional group first. If you look at the C double bond O, it is attached to two carbon, where it's attached to an ethyl group and another ethyl group. Okay, so this is a ketone. So you would expect the name to end with O and E, but the position of the carbonyl compound the carbonyl bond C double bond O is also important. Okay, always name your carbon to give the lowest number of the C double bond O. So in this case, if you start numbering from the left, 1, 2, 3, 4, 5, or from the right, it will still be in the same position, number 3. Okay, so since we have 5 carbon atoms, you would expect it to be called a pentanon. Okay, it's a pentanon, but the position of the C double bond O is on the 3rd position. Therefore, its name is pentan 3-on. Okay. The other molecule on the right, again, I try to identify. This time we've got, it's not really a skeletal formula, because if it was a skeletal formula, then you wouldn't see the CH3. Okay, so this drawing, there's no specific formula for this diagram. Okay, so if we just highlight again the carbonyl group, and it is again attached to 2 carbons. So this is again a ketone. So you would expect the molecule, the name of the molecule, to end with ONE. So I'll start numbering our carbon chain. However, you have to look out for the smaller number. So where are you going to start? And when naming are identifying the principal chain, you have to choose the longest continuous carbon chain. So in this case, if you can see that this is a continuous carbon chain, whether you take this or you take this other methyl group, it's the same thing. Okay, so I want my position of C double bond O to be the lowest position. So I start my numbering with the carbon at the bottom, where the methyl group is. So carbon 1, carbon 2, carbon 3, and carbon 4. So that would give me a principal chain of butanone. Okay, butanone. But again, the position of the C double bond O is important, which is on position number 2. Therefore, I will call it butan 2-on, right? Don't forget our friend here, CH3, who is a methyl, and that methyl is on carbon position number 3. So I have to name a number 3-methyl butan 2-ol. Okay, so this is actually one word. So I'll put them closer. Okay. So be careful with naming ketones or aldehydes with side chain. In this case, your methyl is your side chain. Okay, moving on to the physical properties of your carbonyl compound. So generally, their physical properties would be similar since they are closely related. Okay, when we talk about the boiling points of your carbonyl compounds, just like your other organic molecules, other functional groups, they are all considered under simple molecular structure. Therefore, when we talk about the boiling points, we have to look at breaking the intermolecular forces. Okay, carbonyl compounds will have the instantaneous dipole-induced dipole force. Of course, because this force is present in anything and everything that has electrons. So the first intermolecular force that is present in your carbonyl compounds would be the ID-ID force. ID-ID force, it depends on 2 factors. The first one is the number of electrons and the surface area of contact. Here you have an example of a methanol and a butanol. Both of them are classified as aldehydes because you can see that the C double bond O is at the end in the case of butanol. In the case of methanol, you can see that there's 1 hydrogen attached to the C double bond O, okay? Well, actually 2 hydrogen. The requirement is if you have at least 1 hydrogen attached to the C double bond O, then it's considered an aldehyde already. The number of electrons for methanol is The formula is CH2O and the number of electrons is 16 electrons. And for butanol, the formula is molecular formula. Okay, that's not a structural formula. And it's got 38 electrons. They both belong to aldehyde, but why is it that their boiling point is very different? So obviously, the only factor would be the number of electrons. Butanol has more electrons, therefore the ID-ID force would be stronger between the butanol molecules compared to the ID-ID force between methanol and other methanol molecules. Okay. The other intermolecular forces, the other intermolecular force that is present in your carbonyl compounds, both aldehydes and ketones, is the permanent dipole. That is because there is a dipole on your carbonyl compounds. Okay, this dipole arises because of the difference in electronegativity between carbon and oxygen. So we are going to visit this later on, but for now, you can say that oxygen atom is more electronegative than carbon. Therefore, oxygen would develop a slightly negative, hence delta minus, and carbon will be slightly positive, hence delta plus. Okay. So the boiling point of aldehydes and ketones will be higher than those of similar sized hydrocarbons due to the presence of a stronger intermolecular force, which is permanent dipole. So if you're comparing aldehyde with, say, an alkane or an alkene that has the same number of electrons, yet very different boiling point, for example, looking at methanol and ethene, the number of electrons in ethene is 16 electrons, and in methanol, there are 20 electrons. So they're not the same, but they're quite similar. So you shouldn't expect the boiling points to be very different. However, here you can see that methanol has a higher boiling point than ethene. Okay, remember that it's a negative number, so negative 21 is higher than negative 104 degrees Celsius. This is because methanol has an additional and stronger intermolecular force, which is the PD-PD interaction. Okay, so for ethene, there's only the ID-ID, whereas in methanol, you have ID-ID as well as PD-PD, and we all know that PD-PD is much stronger than ID-ID. Carbonyl compounds cannot form hydrogen bonds, so there is no hydrogen bond in carbonyl compounds, unlike alcohol. In alcohol, you have seen that they can form hydrogen bond between itself, okay, between one molecule of alcohol and another molecule of alcohol, but that's not the case for carbonyl compounds because there is no hydrogen that is directly attached to either F, O, and N. Here you've got your oxygen attached to carbon, so you can't have a hydrogen bond between the molecules. Okay. Next physical property is the solubility in water. Okay. So we have to look at the interaction of your carbonyl compounds. Can they have an interaction with water? They can have an PD-PD interaction, okay? They can also form hydrogen bond with water. Now, even though carbonyl molecules cannot form hydrogen bonds with itself, but it can form hydrogen bonds with water. So you can see here, the hydrogen attached to water is polarized so that hydrogen has a delta plus and oxygen has a delta minus. Okay, this hydrogen is attached to one of the highly electronegative atoms, which is oxygen. So the hydrogen, the slightly positive hydrogen from water, will be attracted or will be forming a hydrogen bond with the oxygen in your carbonyl compounds. Okay, so that's one example where hydrogen bonds can happen. That means if water can form hydrogen bond with carbonyl compounds is soluble in water, but there's a catch. This solubility will decreases as your carbon chain increases. The longer your carbon chain of your carbonyl compounds is, the less soluble it becomes in water. Okay, so that means only small aldehydes and ketones are soluble in water. This is because of the hydrocarbon tails. Okay, the only polar part, or the only part that can form a hydrogen bond with water, is the C double bond O, which we call the polar head. This polar head is water loving. So this is the only part of carbonyl that can interact with water. Whereas the hydrocarbon tail, depending on, but I'm just going to draw a few carbons. So you can imagine the longer the tail is, the more it will dominate the molecule. Okay, so this non-polar hydrocarbon tail is water hating. So this explains why smaller molecule, the more it dissolves, the more it, the happier it is to be soluble or to dissolve in water. Okay. Next, we look at the production of your carbonyl compounds, production of aldehydes and ketones. This is something that we have covered already in the previous topic, topic 16, when we looked at the oxidation of your alcohol, specifically the primary and the secondary alcohols. So they have a different oxidizing agent. You can use acidified potassium dichromate or acidified potassium manganate, okay, and distillation to produce aldehydes. Whereas for the oxidation of secondary alcohol, you can use the same oxidizing agent as well, okay? So alcohols can be oxidized into a carbonyl compound, but only specific alcohol. Primary alcohol will be oxidized into an aldehyde. However, you have to control your reaction. There is a condition. You need to use distillation setup, or we usually write it as distill off, because if you just treat your primary alcohol under reflux without any control to collect the aldehyde, it will be further oxidized into carboxylic acid. So this is something that you have learned already. Primary alcohol will be first oxidized to aldehyde. Aldehyde will then be oxidized further into carboxylic acid. Whereas your secondary alcohol, when it is treated with an oxidizing agent, it will be oxidized into ketone. That's it. That's the final product. So you don't really have to worry about oxidizing your secondary alcohol, because once it produces ketone, which is our desired product, the reaction would stop. There is no further oxidation. Whereas tertiary alcohols cannot be oxidized at all. Regardless of which oxidizing agent you are going to use, they will not be oxidized further. Okay, so they just stay as tertiary alcohol. Just to remind you again on the distillation setup. Okay, so what happens is that you would have your alcohol, primary alcohol here, together with your oxidizing agent. Depends on which one you want to use, acidified potassium dichromate or acidified potassium manganate. So once you heat up your flask, your primary alcohol will be oxidized into an aldehyde. Okay, aldehyde has a lower boiling point than alcohol. So usually aldehydes have low boiling point that it essentially becomes a gas. Once it moves up, okay, it is not able to escape because this setup is an airtight setup, unlike reflux where you have an open mouth at the top. It will then go through the distillation or the Liebig condenser where the gas or the vapor is being transformed into a liquid because this part of the setup is cold. So any gas vapor of your aldehydes will be condensed into a liquid, and so the liquid will drop, or we say will be distilled off and collected. You do not want aldehyde to stay in the reaction mixture because if you have an aldehyde, and then the aldehyde reacts with the oxidizing agent, you will get a carboxylic acid. Okay, this is a problem if you want to collect aldehyde and you don't have a distillation setup, then you wouldn't be able to collect it. You will get the other product, which is the carboxylic acid. Okay, so that is it's important. If the question asks you for the conditions to form aldehyde or to collect aldehyde, it has to be distilled off. Okay, that means you use this distillation setup. As for your secondary alcohol, since the ketone cannot be further oxidized, it does not need to be distilled off straight away. So you can use reflux, no problem. Okay, so going back to the oxidizing agents, I've already mentioned to you what the two oxidizing agents are. The first one, you can use acidified. Sometimes people write down acidified, sometimes people write down H2SO4 or even H+. Okay, it has to be acidified potassium dichromate, K2Cr2O7 aqueous. Okay, so if you want to spell that out, it is spelled as potassium dichromate, but I prefer you to be comfortable with writing down the formula so that it becomes a habit and you will remember it easily. Okay, so the observation is you will see your orange color of potassium dichromate turning into green. That means oxidation process has happened. Okay, so your primary alcohol being oxidized to aldehyde. Now, I don't know if you were taught this, but usually when an oxidizing agent oxidizes another person, in this case, acidified potassium dichromate oxidizes alcohol, itself, the oxidizing agent itself will get reduced. Okay, because in a reaction, when you have oxidation, someone else would have to go through reduction. You can't have a reaction with just oxidation and no reduction. Okay, so it has to be a redox reaction, one species being oxidized, another species being reduced. In this case, it is the Cr2O7, the dichromate ions being reduced. So Cr2O7 is orange. That's the species that is responsible for the orange color in potassium dichromate, is reduced to chromium 3+, which is green. Okay, so the color change is not actually from the alcohol. It is actually from the oxidizing agent. So Cr2O7, 2 minus, sorry, it should be 2 minus, not 2 plus, being reduced to chromium 3 plus ion, which is green in color. Okay, as for the other oxidizing agent, you can use again, it's the same thing, it has to be acidified. Either you write down acidified or you write down H2SO4, or you can even write down H plus with KMNO4 aqueous. So that's potassium manganate. Same thing, acidified potassium manganate will oxidize alcohol, but itself will be reduced. Okay, so you will see a color change from purple to colorless. The explanation for the change in color is because your manganate ion, MnO4 minus, which is responsible for the purple color, is reduced to Mn2 plus, which is colorless. Okay, the purple color is not the alcohol. It comes from the MnO4 ion. Okay, the manganate ions. So because there is a color change, it's something that we can observe. You know that this reaction can be used to identify or eliminate your tertiary alcohol, because tertiary alcohol cannot be oxidized. So you wouldn't expect to see any change with tertiary alcohol. So here's a cartoon diagram showing you the color change for the dichromate ions into the chromium 3 plus ions, and the purple manganate ions to the colorless manganese 2 plus ions when they oxidize alcohol. Okay, itself is being reduced. Okay, if you want to copy this down, you can pause the video here. Okay, moving on. The most important difference in the reactions of aldehydes and ketones is the fact that both of these carbonyl compounds can be oxidized. The difference between aldehydes and ketones is that aldehydes can be oxidized further, whereas ketones cannot be oxidized further. Okay, so we can use this reaction later on to differentiate between aldehydes and ketones, right? If you want to compare primary, secondary, and tertiary alcohol, we know that primary and secondary can be oxidized, whereas tertiary cannot be oxidized. Okay, so this idea is very important. This key point where aldehydes can be oxidized into carboxylic acid, but ketones cannot. Ketones will just stop the oxidation process. This is an important concept in order for us to distinguish between aldehydes and ketones. So here's an example of oxidation of ethanol, which is something that you have already done in the previous topic, but there's no harm in revisiting it again. So we have a CH3, CH2OH. Okay, make sure you practice with your structural formula. Okay, plus oxygen. Plus oxidizing agent. So that's square bracket oxygen square bracket O represent oxidizing agent, because during oxidation you gain electrons. Okay, so I want from primary alcohol to aldehyde. Okay, so just aldehyde, CH3 CHO. So if you cannot see it, just label this as primary alcohol, and you know that primary alcohol will turn into an aldehyde. But there is a special condition where you warm and distill off the product, because if you don't, then the reaction will continue further and you will not collect the carboxylic acid. Okay, the other product you form will be water. Okay, next example is oxidation of propan-2-ol. Propan-2-ol is CH3CHOH CH3. Okay, so you have to be able to identify this alcohol to be secondary alcohol. You react with an oxidizing agent. It doesn't matter which oxidizing agent you use. Since it is a secondary alcohol, you are expecting a ketone. So it's CH3CO CH3, and that is your ketone functional group. This is your aldehyde functional group. That's your ketone functional group, C double bond O attached to 2 carbons. Okay, there is no specific condition for this reaction. As long as you heat it up, you should be fine. Whether you use reflux, whether you use distillation, it doesn't matter, because we're not worried about any further oxidation reaction happening. Okay, if you want to pause the video, you can pause now. Moving on, let's have a look at the chemical properties of the carbonyls. So when we talk about the chemical properties, when we talk about the reactions, it works for both aldehydes and ketones, okay, except for one reaction later on, which is the iodoform reaction, okay? If you can oxidize alcohols into ketones or aldehydes, that means you can do the reverse. So if the forward is an oxidation process, the reverse is a reduction process, okay? So reduction of aldehydes and ketones using sodium borohydride, NaBH4, and lithium aluminium hydride, LiAlH4, to produce alcohols. The alcohols have to be specific. Okay. The condition, sodium borohydride will be dissolved in an alkaline solution. So you use it with either sodium hydroxide. Yeah, usually it's dissolved in sodium hydroxide, and you just have to warm it a little bit. Okay. The second reducing agent you can use is lithium aluminium hydride. Now, lithium aluminium hydride is a more powerful reducing agent. You cannot dissolve it in water. It has to be in dry ether. Okay, so an ether is like an organic solvent. Okay, don't worry about the word dry ether, because you don't want it to be in contact with water. Okay, otherwise there will be a different reaction. It wouldn't be a reduction reaction. Okay, and you just have to use room temperature and pressure. You don't need to warm them, because lithium aluminium hydride is already a strong reducing agent, right? So you can just choose one. If if you are given an option, of course you would choose the one that doesn't require heating. Okay, lithium aluminium hydride. But it's very the handling process is important, because it cannot come in contact with water. It has to be dissolved in dry ether. Okay, right. Reduction process. Unlike oxidation, where you write down your oxidizing reagent in square bracket O, for reducing agent, we write it as square bracket H. That means during reduction, you are gaining hydrogen atoms. So the first example that we're going to look at is for aldehydes. Okay, propanol aldehydes will be reduced to primary alcohol. Okay, so just remember aldehyde will go back into primary alcohol. So the specific example that we have here is propanol, where you have 3 carbons, so that's prop. And since it's aldehyde, the C double bond O will be at the end, at the terminal, and attached to a hydrogen. Okay, so you just transform this part into a primary alcohol. You break this bond, single bond O, add hydrogen, and then add another hydrogen here. It's all about adding your hydrogen and breaking the double bonds into a primary alcohol. Okay, and the number 2 is just to balance the number of hydrogens that have been added into propanol to produce a propan-1-ol. Okay, so this is a primary alcohol because this carbon where your hydroxy group is sitting on is attached to 2 hydrogens and 1 alkyl group. The most important thing is that alkyl group. It's the ethyl group, and there's only 1 alkyl group, therefore it is a primary alcohol. Whereas ketones, you would expect ketones to be reduced into a secondary alcohol. Naming of this ketone, you have 3 carbon, so that's a prop, and it has to end with O-N-E. It's a propanone. You may ask, why is the C double bond O not numbered? Why is it not propan-2-on? Now for propanone, you don't have to number them because there is only one place where the C double bond O can sit. It has to be in the middle. Okay, it cannot be at the end. So numbering the C double bond O in the naming is, we call it redundant. It's like, it's not compulsory. Okay, but if you want to name it as propan-2-on, you can. It's not wrong, but it's not usually named with that. However, if you have butanone, because the C double bond O can be in the well, it can be in the second position. Okay, so you will call it butan-2-on. Okay, same thing here. What happens during reduction is you will break this bond. The C double bond O becomes a single bond. A hydrogen will be attached to that oxygen, and another hydrogen will be attached to that carbon. Now it becomes fully saturated. Saturated means they all contain single bonds. Okay, and this is a secondary alcohol because the carbon where your hydroxy group is sitting on is attached to 2 alkyl groups, 2 methyl groups. Okay. The next slide is just, again, I've mentioned this, why lithium aluminum hydride needs to be in dry ether. It cannot come in contact with water, otherwise it will react vigorously with lithium aluminum hydride and reduction reaction will not happen. Okay, now you may notice the reduction reaction, unlike your oxidation, there is no observation here. Okay, everything will be colorless. Sodium borohydride will be colorless, lithium aluminum hydride will be colorless, so you do not have an observation here, unlike your oxidation process. Okay, let's have a look at the example of reduction. First thing to do is to identify your functional group. You've got a C double bond O attached to a hydrogen, so that must be an aldehyde. And we know that aldehyde will be reduced to primary alcohol. So you just have to worry about the highlighted part of the molecule and change them into a primary alcohol. The rest of the molecule stays unchanged. So that means I'm just going to draw the parts that don't get changed during the reduction process, okay? And then COH, that's the original molecule. Just add hydrogen onto the oxygen because you've broken the double bond, and add hydrogen to the carbon just to complete this carbon to have a 4 bonds. Okay, if you want to balance this equation, it would be adding 2H. Next, again, try to identify the functional group. So I've got C double bond OH. Okay, now even though the chlorine is there, don't be distracted by it. Okay, just highlight the functional group that will get reduced. So we've got an aldehyde. Again, it will be reduced to primary alcohol plus reducing agent to produce, keep everything the same. Okay, and this is the original part of the molecule, but because the reducing agent has supplied the hydrogen, you've got the hydrogen atoms being added to your molecule. Okay. Lastly, this is a skeletal formula. And if you want to identify the functional group, we've got C double bond O attached to 2 carbons. So this would be a ketone. And ketone will be reduced to secondary alcohol. Same thing, plus 2 hydrogen atoms. That represents your reducing agent. And I'm going to keep the original atoms in the molecule and add on the hydrogen there. Okay, the rest of the molecule stays unchanged. Now I have a secondary alcohol. Okay, so if you need to copy this down, you may pause the video now. Next reaction, we're going to look at the addition of hydrogen cyanide. HCN is called the hydrogen cyanide. So during this reaction, you will see that your carbonyl, whether it's an aldehyde or whether it's a ketone, will be transformed into what we call a hydroxynitrile. Okay. The learning objective for this one would be the reaction of aldehydes and ketones with HCN, which is your hydrogen cyanide. Let me just write it down. With your potassium cyanide as catalyst, you need to heat the reaction and to produce hydroxynitrile. So examples that you're going to use will be ethanol and propanone. Okay, describe the mechanism of the nucleophilic addition. So that is a hint for the name of the mechanism, nucleophilic addition. So far, you have come across electrophilic addition of alkenes, nucleophilic substitution of halogenoalkanes, and now nucleophilic addition. Okay, so This is something new for you. Okay. So aldehydes and ketones can undergo a nucleophilic addition with hydrogen cyanide. So that's the name of your mechanism. It's important for you to remember that. The catalyst will be the cyanide ion, C triple bond N with a negative charge, and the lone pair comes from carbon. So cyanide ion is not something new for you. You've met cyanide ion in halogenoalkanes already, okay, where you use potassium cyanide or sodium cyanide dissolved in ethanol for the nucleophilic substitution of halogenoalkanes, okay? So your cyanide ions continue to act as a nucleophile, hence the name nucleophilic addition, and acts across the C double bond O bond. Okay, so what does it mean to be added across the bond? You'll understand when you look at the mechanism later on. Okay, unlike nucleophilic substitution, there's no substitution happening here. Instead, you have an addition. The reason for this is because your aldehydes and ketones are unsaturated. It contains a double bond. So you can add atoms to the double bond, just like your alkenes, electrophilic addition. Okay. Aldehydes and ketones react with HCN with the presence of a catalyst, which is your potassium cyanide or sodium cyanide, and heat to produce hydroxynitriles. Okay. So what happens here? We're going to look at ethanol as an example of aldehyde and propanone as an example of ketone. Okay, I believe you have this in your notes. Okay, right. So the reagent is the HCN. The catalyst is your potassium cyanide or your sodium cyanide. Okay, what happens is that your C double bond O will break as a single bond, and your cyanide ion will be added to that carbon. Okay, so if I highlight your cyanide ion, then your cyanide ion ends here. The new bond being formed is this carbon-carbon bond, single carbon-carbon bond. This is the new bond being formed. Your oxygen is still here, okay? But instead of having a C double bond O, it now becomes a C single bond O, okay? Maybe I want to change the color, sorry. The yellow is the CO bond, and the blue bond is the new carbon-carbon bond being formed. Okay, so this is new bond form. Okay. For ethanol, you have two carbons, okay? And then in the product, which is called the 2-hydroxypropane nitrile, we've got three carbons, 1, 2, 3. So this reaction is an excellent reaction if you want to add one additional carbon to your molecule. Okay, so you start from 2 carbons in ethanol and you end up with 3 carbons in what we call a hydroxypropane nitrile. Okay, so how do we name this molecule? First, we need to identify the principal chain. Oh, I'm not sure if that's a great color to use. Yellow. I'll change it. Pink. Okay, so this is your principal chain. Which is called the propane nitrile because it's got 3 carbons. 1, 2, 3. So we call that a propane nitrile. Okay, so you've got propanenitrile. Next, we want to identify the side chain, which is your hydroxy group. Okay, why is it not alcohol? Well, now the nitrile wins over the alcohol, so we don't call this an ethanol or something. Okay, so we want a principal chain with the longest carbon atom. If you take the alcohol, for example, if you just take this, then you have 2 carbons and that become ethanol. If you take the nitrile as part of your chain and then it becomes the principal chain, you now have 3 carbon, which is the prop. Okay, sorry, 2 carbons. I don't remember what I said just now. 2 carbons would be ethanol. Okay, 3 carbons would be prop, and it's called a propane nitrile. Okay, so that's why we call it a 2-hydroxy propane nitrile. Let's have a look at propanone to represent a ketone. Okay, so you can see clearly the difference, right, between a ketone and an aldehyde. A ketone would have the carbon attached to 2 carbon atoms, whereas an aldehyde will be attached to at least 1 hydrogen. Okay, same thing. You've got a hydrogen cyanide with your catalyst in the form of potassium cyanide, and then the CN will end up here being attached. The new bond being formed is the C single bond C. That is your new bond. What happens to your carbonyl, C double bond O? It now becomes a single bond. Oops. A single bond O, and it is attached to a hydrogen. Okay, so you'll only understand this when we look at the mechanism later. Naming. Again, I want the principal chain to include the C triple bond N. So my principal chain will be this. Number 1 has to be at propane nitrile, at the nitrile group, sorry. 1, 2, 3. Okay, so that's the principal chain. Nothing new. It's got 3 carbons, so it's called propane nitrile. Oof. Prop. Okay, so that propane nitrile. And then my side chain, if I use blue, this is my side chain on carbon number 2, and this is my side chain on carbon number 2 as well. So I call it, I guess if you follow the alphabetical, the hydroxy should come first because it is H followed by M. Okay, so I will change that to 2-hydroxy, 2-methyl propane nitrile. Okay, this is hydroxy and CH3 is methyl. Okay, why have I changed it? Alphabetical orders. Alphabetical order. Okay, but of course, if you call it 2-methyl 2-hydroxypropane nitrile, it is not wrong because the position of the hydroxy is in the correct position, which is carbon number 2, as well as the methyl, which is on carbon number 2. Okay. Before we look at the mechanism, we're going to cover the theory first of carbonyls and why does it undergo nucleophilic addition. So first things first, I've already mentioned this just now, carbonyls are unsaturated. Unsaturated means contain double bond, which is the C double bond O, okay? So because of this unsaturation, addition will take place across the C double bond O. So you can see just now, we are adding, the C double bond O will be broken. The carbon will be attached to C triple bond O, and the oxygen is attached to the hydrogen. The next concept, the C double bond O is a polar bond, okay, in both aldehydes and ketones. Therefore, it develops the dipole, oops, C double bond O, whether it's aldehyde or ketone, delta plus, delta minus. This is due to the difference in electronegativity. And we know that oxygen is more electronegative than carbon. Okay, so why do we talk about this polarity? It's because the slightly positive carbon attracts nucleophile. Okay, remember, nucleophile is a species that can donate its lone pair. Sometimes nucleophile is neutral, sometimes nucleophile is charged, negatively charged. So nucleophiles will like to attack an atom or a species that is lacking in electrons. For example, C delta plus. Delta plus means it's lacking in electrons because the electron density is saturated on the oxygen. Okay, so, or you can just imagine nucleophile having a negative charge, whereas the carbon having a delta positive charge. So opposite charges attract. For the third point, this table is just to show you the difference between the two mechanisms of your carbonyls and alkenes. Both of them contains a double bond. So that's why they will result in addition reaction. Okay. The difference is in polarity. Your alkene, C double bond C, there is no difference in electronegativity. So we say that this bond is nonpolar. But when you look at the mechanism in topic 14, was it topic 14? Yes, topic 14, you should have seen that an instantaneous dipole will be produced, okay? Whereas in carbonyl, C double bond O, you have a permanent dipole, and we call this a polar bond, right? And of course, they are attacked by different species. Alkene is attacked by nucleophiles. Carbonyls is attacked by, alkenes is attacked by electrophiles, whereas carbonyls are attacked by nucleophiles. Okay. Right, so we're going to look at the mechanism on how we can convert your carbonyls into your hydroxynitriles. Okay, so the example that we're going to use later on will be propanol. So this is the equation. This is the correct equation of propanol reacting with HCN to form a product called 2-hydroxy 2-methyl propane nitrile. Okay, so if you just copy this equation first on the top part of your page 6, now, since I have two formula here, I'll show you. Well, this is actually a mixture of structural and displayed formula. Okay, it's not strictly displayed formula. It's also not strictly structural formula, but this one is strictly structural formula. So a lot of you still get confused with displayed formula and structural formula. Even though the name is structural formula, where you think that you have to draw the structure, it's actually writing down the formula like this, okay? Right, notice that an additional carbon atom has been added to the product. In the starting material, you have 3 carbons in your propanone, okay? Sorry, I said this was propanol, right? This is propanone. Propanone. There are 3 carbons in the propanone, but in your products, there are 1, 2, 3, 4. 4 carbons, including the carbon on the cyanide, CN, nitrile functional group. Okay, so when naming hydroxynitriles, CN becomes part of the main chain. That's why we always start our number at the carbon of C triple bond N. All right. So your reagents would be either sodium cyanide or potassium cyanide with sulfuric acid. Now, previously I mentioned that the reagent has to be HCN. The problem is that HCN, hydrogen cyanide, is a very poisonous toxic gas. You cannot transfer or put hydrogen cyanide in a bottle. You have to make it on the spot. Okay, and this is what we call in situ, which means we produce the hydrogen cyanide inside the reaction vessel, and in order to produce the hydrogen cyanide, you will have the sodium cyanide or potassium cyanide reacting with the sulfuric acid at room temperature. Okay, room temperature and pressure. No need to heat it. Okay, so let's have a look at the mechanism. So now the example wants you to use propanol. Okay, so I don't know why I have different things, different molecules, but it works. If it works for aldehydes, it works for ketones as well. Okay, so I will have a propanol, and I need to be careful with my color codes. Did I? Okay. Right, so the first step is to have my propanol ready. I think I'll end up drawing everything on the same slide. So propanol means I have a C double bond OH, that's the most important thing. And then I have CH2, CH3. Okay, so that's propanol. Don't forget my dipoles. I should always have my dipoles at the start of the reaction. Okay, and then my my electrophile, my nucleophile is the cyanide ion, which has a negative charge and has a lone pair on the carbon. So the cyanide ion will attack the slightly positive carbon. That means the lone pair on the carbon has been shared with carbon, the slightly positive carbon of the carbonyl group. Okay, so you would imagine that there will be 1, 2, 3, 4, 5 bonds here. Okay, so that means we need to break one bond, and the bond broken is one of the C double bond O. Okay, so when this bond is broken, the electrons has to go to the more electronegative atoms, which is the oxygen. Okay, so that's step 1. Do I have space? Step 1 is the nucleophilic attack. What do I form here is an intermediate that looks like this. Carbon with CH2, CH3 that stays unchanged. My hydrogen at the bottom. The new bond being formed with C triple bond N, the negative charge is now gone because it has been moved to the oxygen. Okay, so it is important that you draw the lone pair of electrons and the negative charge. Okay, this goes back to our heterolytic fission. All right, the atom who gets the lone pair, the person who gets the pair of electrons become negative, and the person who doesn't get the electrons becomes positive. So if you imagine this carbon becomes positive, combined with the negative charge on the cyanide ion, this part becomes neutral. Okay. So I've broken one of the double bonds in C double bond O to become a single bond CO single bond. Okay. Next is the step 2, where we have what we call protonation. Protonation means the acceptance or the receiving of a proton. Now, proton is H+, okay? We haven't learned this because we haven't covered acids and bases yet, but H+ is actually also called proton, okay? So this H+ comes from your HCN. I'll use green. Okay, so HCN will also be a polarized molecule. Okay, the lone pair on oxygen is donated to the hydrogen so that it can form a bond with the hydrogen, and the HCN bond has to be broken because hydrogen cannot form more than one bond. Okay, so if it forms a bond with oxygen, it has to let go of cyanide, the CN part, which is the cyanide ion. Okay, so in step 2, you will get this carbon with CH2, CH3 that stays unchanged. The hydrogen also stays unchanged. The nitrile is already happy in that molecule. So the last thing is just to complete the diagram. Single bond O, and then we have a single bond oxygen with hydrogen, and the other species produced is the cyanide ion. Okay, so you notice that we used up a cyanide ion and then we reproduce a new cyanide ion. So cyanide ion in this case is what we call a catalyst because it stays unchanged. At the start, you have a cyanide ion. At the end, you also have a cyanide ion, even though we know that it's not the same cyanide ion, but because you get the same thing back at the end of the reaction, this is the definition of a catalyst. Okay. Right. I'm just going to add some annotations. This intermediate, this tetrahedral intermediate with a negative charge is called the intermediate. Of course, there's no, you don't have to name it specifically. Naming the final molecule. So look at the principal chain. We've got carbon 1, carbon 2, carbon 3, carbon 4. So that is a, oh yes, this is a, I'm afraid there's something wrong with the name. Propan, it's not propanitrile, it should be butane nitrile. Okay, can you change this part where you can find it in your notes? Change that. It should be not propane but butane, because you started with 3 carbons and you have to end up with 4 carbons. You can't have the same number of carbons because you've just added your nitrile group. Okay, so that is a butane nitrile, and your side chain is called the hydroxy group. Okay, I do not have a methyl group. I think yeah, it's not called that. So my hydroxy group is on position number 2. So it's a 2-hydroxy butane nitrile. Okay, so let me see, that's ethanol. Yeah, correct. 2-hydroxy butane nitrile. The number has to start from the CN group, because now the CN becomes a part of the principal chain and it has to have the lowest number. So 1, 2, 3, 4, hydroxy group on carbon number 2. We call it 2-hydroxybutane nitrile. So please change the name that you have on your notes, propanol plus HCN, to give you 2-hydroxybutane nitrile. Okay, so if you want to copy this down, you can pause the video here. Okay, when you're done, I also have another example here. If you want to look at ketone, okay, so this is not propanol, also not propanol. This is a propanone reacting with hydrogen cyanide to form. So if I name this, so that's carbon 1, carbon 2, carbon 3. So that is a propane nitrile. And I've got methyl and hydroxy. As my side chain. Maybe I should just draw it as dotted. So this is what we call a 2-methyl 2-hydroxy propane nitrile. Okay, why is the name here starting with hydroxy first, then methyl, whereas I've written it as methyl first followed by hydroxy? Well, I have followed the alphabetical rule where no, that's not the alphabetical rule. Sorry about that. It should be hydroxy first. I'm confusing myself here. Yeah. It should be hydroxy first. Sorry about that. So 2-hydroxy, 2-methyl propane nitrile, because of the letter H coming first, followed by the letter M. So sorry about that. So in your notes, it's correct, 2-methyl propane nitrile, but the problem is here, okay? Here's another example where you can use ketone as well for your nucleophilic addition mechanism. Okay, the steps is the same. Your cyanide ions attack the slightly positive carbon where it shares its lone pair to form a new bond, carbon single bond carbon bond. This carbon cannot have 5 bonds, therefore one of the double bond has to break and the electrons go to the more electronegative element, which is oxygen. Since oxygen has gained the pair of electrons from the bond originally, oxygen will obtain a negative charge, and in order to neutralize this negative charge, it has to combine, or it has to give it away to a hydrogen plus, which we call a proton. Okay, then you get your products, which is called a 2-hydroxy 2-methyl propane nitrile. Okay, so this time you've got 1, 2, 3, 4 carbons in the product, whereas in the starting material you only have 3 carbons. Okay, so you can copy this down if you have space. Just make sure you label them correctly. Propanone, I believe you have space at the bottom of page 6, and you can pause the video here. Okay, this slide is showing you the mechanism of a ethanol. Okay, so if you want a different example, you should be able to see that they basically have the same steps. They follow the same arrangement of attack. Okay, first the cyanide ion attack first, and then one of the double bond breaks. Oxygen then develops a negative charge, and oxygen has to pick up a proton or a hydrogen ions from HCN to produce a hydroxynitrile. Okay. Right, so that is all for today. We will continue in the next lesson with iodoform reaction, and also test for carbonyl compounds and how to differentiate between aldehydes and ketones. Okay, Assalamu alaikum and thank you.